Before we go totally live, by the way, this is your last chance to grab a donut or two. I understand they are plentiful up there, and you might be able to reach a bargain with the purveyor thereof. Just a word to the wise, it is the holiday season. Okay. Okay. We on? Okay. Welcome everybody to the last meeting of Orange County Astronomers for the wonderful year of 2023. This is our December meeting, and we've got a nice group here in the auditorium at Chapman University, and I think a nice bunch of folks online. Welcome to all of you. And our regular announcement person is not here, so I will be purveying the announcements before we get to the real guts of the meeting. We have a wonderful What's Upper as well as a wonderful main act, and basically I'm regarding this as a wonderful two-header, but we will get into that later. Right now, as I said, welcome. This is somebody else's computer, so bear with me while I find the controls. Okay. We have some new members. Welcome to all of you. If you are here in the auditorium, do check the badge thing down here by the whiteboard. If you are not in the auditorium and not planning to be in the auditorium, Charlie Osteich will be sending you your membership badge in the not too distant future. You sharing? Getting the noise. Yeah. Oh, okay. We're adjusting on the technical side. Okay, we have star parties. Well, at least we have a star party. Tomorrow night is our ANZA star party. This is the regular one. Remember, ANZA is open 24/7 to members in good standing. But star parties are always kind of special. Unfortunately, tomorrow night may be special in the wrong way, as the forecast is for wind. So please bear that in mind. Check out the weather before you go out there. Oh, by the way, on the Orange County star parties, periodically people do ask about those. We are working on getting them back in regular on our regular format. We are trying to work out some details with the with OC Parks, but we're hoping that with the new year we will be back on board with those as well for those of us that want to go to the more local star parties. Outreach events are currently on hold, but we are busy revamping the program somewhat, and we do need a new coordinator who is interested in running the program more along the lines that we have traditionally had, which would involve more member volunteers, and ideally taking telescopes out to schools and sharing them in the way that all of us that have done outreach in the past have totally enjoyed. So if you're interested in the outreach coordinator position, do please send an email to Alan Smallbone, our current secretary, and we're hoping one way or another we're going to be getting that program going again. Now, I mentioned a couple in the last couple of meetings. Just to remind you, we do have an election on. We have one at the end of every year. You should have received a ballot with the with your December series Astronomer. There should also be ballots available online on the website, and John Hoot will be sending out emails with the electronic version, which many of us have found to be a whole lot more a whole lot easier to use, shall we say, than the hard copy version that you have to put in an envelope and do all the necessary things with to protect confidentiality and all that. So one way or another, please get your votes in. The election ends at the end of the January meeting. So you got like a month, and that will let the board, including me, know that you are keeping an eye on us, which is good to remind us of, right? This actually is the list of the people who are running, and you may notice that we do have at least one person for every position, which is great. You will notice on the ballot, you also have the ability to write in a candidate if you would like to do so. One way or another, please let us know where you stand. The Adopt a Scope program under the guidance of John Hoot has been a tremendous success. And probably he is the victim of his own success. He has advised us that in the interest of domestic tranquility, he needs to step back from that somewhat. But it looks like we have a new candidate who will be taking that over. So you will be seeing some changes in leadership on that. John will remain involved to make sure that it continues on track. If you are interested in a scope through the program, they are listed online. And there'll be notices posted as well about when the next event is for adopting a scope and so on. Then on the Serious Astronomer, you may remember getting that every month. That is our newsletter. It has been with us since I think the earliest days of the club. And if you want to continue receiving a paper copy, that's wonderful. If you would prefer to get yours electronically, then that is also an option. Just let Charlie know, and he will modify the membership records accordingly, and you can get yours online. Some people prefer that because they want to save mailing and they don't want the paper piling up. Other people just love the paper. Okay, that's what this slide was about, actually. Anza weed clearance. Hopefully the weeds are slowing down. I haven't been there for probably 6 weeks. So but do keep an eye out when you are out there. If you see any encroaching on buildings or anything like that, please do us a favor and help get them back. If we do get a fire out there, the more defensible area we have around our structures, the less likely we are to have serious damage, and the easier it is for firefighters to actually protect our property. We don't have our usual announcer regarding the moon, but we are reliably informed it is a waning crescent tonight and aiming toward new moon in a few days. You may be hearing more about that shortly. The next meeting, which is the end of the election, is January 12th of 2024, New Year. Things getting off to a great start. We'll look forward to seeing all of you then too. And that leads me to the next great announcement, which is our doubleheader. We have John Garrett from the Temecula Valley Astronomers, who is doing our What's Up program. And our featured speaker tonight is Chris Butler, who many of us have known for many years and enjoyed many talks from. He is with Griffith Observatory, and we'll be talking about Brave New Worlds. So without more ado, let me turn this over to John Garrett, who is one of our favorite What's Uppers, and we are very glad he's willing to make the trek out here. Welcome, John.
Thank you. I do want to say that maybe it's about 20 or 15 years ago, Chris Butler did a presentation at my astronomy club, the Temecula Valley Astronomers, and that inspired me to do the kind of outreach that I do. So I owe him a big debt. So I just wanted to say that. Anyway, so on this first picture, this is the of the dark sky images I might show during my presentation. I just want to show what scopes I use to take those pictures with. And the small one I often refer to as my TV 76, TeleVue 76. It's a 3-inch refractor. And all the pictures I take with it are usually just with a focal reducer and at not prime focus, but prime focus reduced to a shorter focal length. Yes.
Sorry to interrupt. Looks like you have the wrong presentation shared online.
Yeah, you need to share your presentation.
Oh, okay. Thank you. Okay. I see something that says stop share. Okay. So I'm a little confused.
And then reshare with the slideshow.
Okay. Yeah, it's always nice to do a nice little restart so I can kind of begin again. Yeah. Okay, are we good?
Yes.
Yes. Oh, thank you. Yeah. Anyway, so and then the other photos I've taken with my 8-inch telescope. So throughout the presentation, I'll have little references to those two scopes, and that's what I'm usually using. I do a little bit of stacking, but I still prefer to just take the scope, aim it, take about a half minute or minute exposure and see what shows up. It's just a quicker use of time. So anyway, okay, what am I hitting wrong? I'll try it. Okay, sorry. Okay, that time of year. One of the challenges of doing the What's Up for December is that we encounter a lot of conflict with the weather. So it's been rather difficult to get fresh photos of a clear sky. And so I took this one earlier in the week. But the main reason of what you see here is the moon making a 22-degree halo around it. You often see that around the sun, and you see that around the moon quite often, especially this time of year when we get a lot of icy clouds coming in. But the reason I took this one, I had to get this picture taken, was that I saw Jupiter in the picture. So Jupiter's there far up on the right. And I realized, well, we're always given advice as to how to use your hand or your finger or something like that to estimate a degree of separation in the sky. Well, here's one naturally that occurs. So that's a 22-degree difference between the center and the edge. And so I was thinking, wow, wouldn't that be neat if I could calculate whether Jupiter, how far past opposition it is based on just this, because a degree roughly corresponds to a day of motion. And in my back of the envelope calculation, I think that Jupiter was like 24 days past opposition. And if that was actually the moon at opposition, well, it's pretty close to 22 degrees from where the moon is. And so it's one of those things that it's probably falls in the category of how to do something the hard way. If you got a phone, you could probably take this picture and then just look up, is Jupiter at opposition? But it's kind of fun to think about what natural tools you get in the sky through astronomy to work out those things. And just last weekend, we had an incredible day of what we would call parhelia, and that is optical effects created by this cloudy weather. And so there are 7 different optical effects in this picture that I snagged with my iPhone, things that you might want to look out for. The circumzenithal arc, that's that one that's up way high, looks like a smile. Then the supralateral arc, it bends down. It actually forms a big circle around the sun. And then the peri arc, which was new to me, I'd never seen it before, that forms a little frowny face. And then right below that is the tangential arc. And that one usually sits like a pair of horns on top of the 22-degree halo around the sun or the moon. And then there's a faint 22-degree halo and also a sundog. And something I'd never looked up before, but sundogs often have tails. Well, that tail is also called a parhelic arc. And so I ran in after taking about a dozen iPhone pictures. I went in and got my other camera to try to get some better images of it. And here you can see the parhelic arc. This one, it actually extends toward the sun and then extends out a ways from the sundog. So that's an effect that you might see a big, huge ring passing right through the sundogs, through the sun, and then out the other way. And then here's a close-up of the other arcs, that the tangential arc and the peri arc and the supralateral arc and the circumzenithal arc. And so this is one of my favorite shots so far now of that phenomenon. I've never been able to catch 2 of them like this in one thing. So bad weather, but good for things like this. So keep looking up even in the daytime. And even I think you might be able to see these things at night with moonlight too. Okay, morning sky. I got up to check on Venus. And so there's Venus pretty high in the morning sky, but it's going to be setting really fast. And so by the end of the month, Venus is going to be out of our sight. It's probably not the best object for a telescope right now because it's moving away from us, getting smaller, getting full, and disappearing behind the sun. But the getting up early in the morning, even though Venus might disappoint, is still a long-held tradition of people have done it for probably thousands of years to use the first appearance of a star, of known stars in the eastern sky before sunrise. It's a term called the helical rising as a marker of the calendar. And so I've been able to see in the past month that these 2 constellations, Virgo and Corvus, have probably had their helical rise. And it also marks the beginning of an entire observing season for these constellations as they slowly move higher and across the sky until they disappear in the west for the year. And so if you're getting up might want to look at a couple of favorites. I've drawn Virgo as a student in microbiology reading a book. I think Virgo looks like someone reading a book, so I'm always going to put a book in there. And I used Venus as her foot. And so as she gets tired reading, her foot will stretch out, which just means that Venus is going down to the horizon. But anyway, in this area are three projects that I plan to take up. M104. I haven't taken a very long stacked version of this before. This is just a single exposure with my larger scope, but it's a beautiful galaxy. If you haven't seen it, do. But you've got a whole season of it being present in the sky to look forward to. And then here's a globular cluster right over there below Corvus. And something I just discovered fairly recently is a planetary nebula in Corvus. So if a planetary nebula for my equipment, if it shows up as having any size to it at all, it shows that it's probably a promising object for a little more work, for a little more stacking, and also a little bit getting out to a darker sky to see that. So I've got most of a year to do that. Comets. We have two comets in the night sky. I had one clear morning where I tried to get out and get a photograph of one of the comets that would be in Leo right now. And it just so happens that's where the moon was, almost exactly. So I'm using this picture of the moon in Leo taken earlier this week to show exactly where the comet was. It was right behind the moon there. And over the next month, it's going to move over to that star in Leo. So it's something you might want to look for. And while you're up there, this comet is going to be a telescope object only. So you might want to also look at these other telescope objects, these galaxy clusters. And then here's another comet. I tried to take that this week under very poor observing conditions. And so this is taken with my 3-inch refractor. It's comet, actually my display is hiding the text. I need to remind myself which one it is, Pons Brooks. This one had some outbursts in the last month. So it had got some chatter on the internet about brightening. And so I tried to get some pictures after it had done that. But so it's a good one to watch. It's in the evening sky. This was taken with my 3-inch telescope. And that same night, I switched my camera to my 8-inch telescope. And by the time I got everything focused and was taking a picture, I was looking at it and go, I think it's going behind the roof of my house. So that's what you actually see here. You see the comet and the roof of my house rising into the picture. My wife recommended that we need a slower house, and I probably would have gotten this picture. But here's how it looked with the same equipment a couple weeks earlier. So this is something that you might expect in the evening sky. I'll show you where that is in just a moment. And so we have a couple good one good meteor shower. The others I don't know about. Possibly 3 meteor showers this month. But there's the Geminids, a regular favorite. And they also peak on the night where you have a negligible moon. So if you are free to take off on Thursday, take off work, or lie about being sick or something like that, staying out that night might be a very promising night to watch for the Geminid meteors. And then the Ursids, they're supposed to peak around the 22nd. And where I wrote maybe 10 per hour, that was an optimistic estimate. But another thing to look for, I don't ever want to tell someone not to look for a meteor shower. But there was a time when I got my wife to set up with me in the cold and winter to watch a meteor shower and didn't see any. So be warned, if you give someone bad advice on that, you might have to live with that for a while. Anyway, here's a Geminid in Orion that I probably caught about 10 years ago. And here's what might be an Ursid. I wasn't entirely sure. There's so many satellites in the skies, and a lot of satellites do start out dim, brighten, and then dim again. So I don't actually believe a meteor unless I see it or can actually pick up some color in the photograph, but it might be an Ursid. And then there's a comet. About 5 years ago, we had this comet 46 Wirtanen on one of those nice green comets, and there is some speculation that it might produce a meteor shower this year. And the best time to see it will be in, actually the best place to see it will be in the southern hemisphere. Okay, so you can't see what I'm saying. I just looked up there and realized that that's blocking all the notes that I gave. So I wrote up there all the things that I tend to forget to say in person. And so we're going to try to see if we can do that without, that's brilliant. Okay. So, evening of December 12th would be the best time to see it, but it also is expected to be best viewed in the southern hemisphere, but it's a brand new potential meteor shower. So who knows what we'll see. And Okay, now we're not moving. Okay, click on the screen again. All right. Okay. Okay, good. And a little bit about the evening, what you might see in the evening sky. So here's a view from my driveway, and this is looking toward the west, and you can see the summer triangle is still in the sky, but also getting lower each night. And that puts the summer constellations in their upside down position. So the two birds, Aquila and Cygnus, are doing nosedives, and Delphinius is doing its backflop. And but anyway, over here down by the star Vega is the constellation 12P Pons Brooks. So that's the one that you might want to try to find in the evening sky. Right now, this weekend, look near the star Vega is your best chance of seeing it. And over the next month, it's supposed to travel up this way. So it gets a little higher. However, my house goes up a little higher too. So each night, everything sets lower, making my house a little higher, but it will stay above the western horizon for the rest of the month. And since it's been prone to some outbursts, it's worth watching. Many of you could be the first one to catch one of its outbursts. So now swinging around, I'll notice how clever it was of me to take my notes and move them to the top of the screen now. And so I didn't do it for many of them. We'll just leave it like this. We'll just leave it like this. Okay. It's an excellent time to view Jupiter. You go out in the southeast and Jupiter sits really high and just gets higher. And in a few hours, it's almost straight overhead, which is a good thing if you want minimum atmosphere. It's a bad thing depending on the type of telescope you have and how easy it is to crane your neck and look up that way. But it's an excellent time to see Jupiter. And here is a view where I put together three photos to give you a view of the four outer planets where they are in the sky. So the ecliptic is approximately there, and what I've drawn starts through Jupiter and ends over there in Saturn. Saturn is a little higher in the sky, but it's also working its way down in the evening. Saturn is getting away from us. Its rings are getting more edge on, but if you look at it with over 100 power, you can still see definition of a ring. You can still see a gap next to Saturn inside the rings. We had a star party last night, and it featured very well that way. And here's where I estimate all the planets are. Jupiter and Saturn are obvious where they are. Neptune, I haven't looked at Neptune, but it's up there, right where I've shown here with the blue planet. And then Uranus is just trailing right behind Jupiter, way off on the left. And I haven't looked at it through a telescope, but I did take this exact same photo. I blew it up and just to see if I could see Uranus. And so in that crosshair that I have, I bumped up the saturation so it might show as a green planet, but I hope you can see that right there in the corner, an obvious green planet. So it shows up using a cheap lens, so it should certainly look nice in a telescope. Anyway, here's a Jupiter in my larger telescope from this week. And I never get tired of looking at Jupiter or Saturn, even though I've seen them time and time again. And of course, the human eye does something better than what my camera can do. And the human eye, you can actually see Jupiter as though you were taking it at a faster shutter speed, as I've done there. And now I've spliced those two images together and blew them up a little bit. But this is more the impression that the human eye gets when you look at Jupiter. So I definitely encourage you to look at it through a telescope while it's looking really good. And so here we've got Jupiter. Not far below Jupiter, you'll find the Pleiades, which is usually the herald of the winter constellations. And I'm not covering the deep winter constellations tonight, just a few that are overhead near sunset. Jupiter is still near constellation Pisces and in the constellation Aries. And here I'm misdrawing Aries because I'm drawing it the way I see it. When I see those stars in the sky, I think, oh, that looks like a ram, that group. But that group of stars is actually three constellations altogether: Andromeda in red, Triangulum in green, and then Aries is that little thing. I don't even know what to call that, but that's how they often portray constellation Aries. Anyway, in that area, I took an interest in four deep sky objects because they're fairly new to me. M33 is actually well known, one of our major galaxies in our local group, a beautiful edge-on galaxy that's very faint. But the others are ones that I haven't really spent any time with before. And so here's how they might look. And this is a NGC 524 in my 3-inch refractor. And it doesn't look like much. It looks like it's a little tiny dot, but on my camera, I can see that there's a whole mess of galaxies right around it. So that makes it a very good target for a little more deep soaking of the image to see if you can get out image a group of clusters, or what you might see with a larger telescope. And then this one here is M74, which I haven't really looked at before, and I'm not really doing a great job of imaging it. And so it's always nice to have a lot of improvement that I can do later. But it has a nice spiral to it, and has a nice good size to it in an 8-inch scope. So definitely worth looking at. And then here's that open cluster, was that NGC 752. And then M33, also most of these, I think all of these I photographed from my driveway in Wildemar. So I got significant light pollution. So I'm working against that. So you get out in a dark sky, you can do all kinds of wonderful things with it. This last image is just pointing toward the eastern sky, because we're always looking east to see what's coming up new. You might be able to trace out Cassiopeia on the left, which if I went into Cassiopeia, there would be dozens of objects to look at. But it also is a nice marker that the winter constellations will be overhead really soon. Anyway, thank you for the opportunity to share that.
Great. Thank you very much, John, for yet another great presentation, telling us about all we can see during the upcoming months. So let me, without any further ado, go ahead into introducing our main speaker of the night. Our speaker tonight is an internationally published science and nature artist, best known for his work on astronomical subjects and for his work as a science speaker and educator. He is the senior artist and animator for the Griffith Observatory in Los Angeles, where he has been involved in public program production and exhibit design for 26 years. He has an asteroid named after him by the International Astronomical Union. And he has been a member of the Orange County Astronomers since 1984 and has served as vice president and a member of the board. Please join me in welcoming our very own Chris Butler. Chris.
Pardon, Father Christmas. All right, which one what am I? I don't know. Which one's so good? Wait, let's see. Where are you? Not on the radar here. Not any of those. Okay, well, we're going to find a presentation for me to do here. There are a number of them, some on healthcare and insurance. Yeah, right. The HMO for OCA. All right, well, just. I need a microphone? Well, for the folks at home, I do. Yeah, I need to minimize this sucker. For the folks at home and all of us here in the audience, we remember live from ANZA, do we not? We're getting off very lucky. This will not be that bad, I promise. Oh, yeah, all right. Well, yeah, I did a fake broadcast live from the moon once. And I did one from Mars as well, actually. But the light speed delay was really annoying. Here he comes.
I was standing in the back when you did live from the moon. I was standing in the back there when he did live from the moon, and up on the screen was Chris on the moon, and I believed it. And my brain said, that's Chris on the moon. And Helen was down here talking to him, and they had it figured out. It was perfect. It's the coolest thing I've ever seen. Finally, about 5 minutes in, my brain said, this is a put on.
Well, there's a couple put-ons that most members of the club actually don't yet know about. There's one that's 35 years long going now, and no one's figured it out, which is in the OCA image gallery. There's a picture in there that is not real. Just so you know. I'm waiting for somebody to spot it. Would you like that? Where would I? That's good. Let's do that. Yeah, no, I'm good. I'm highly flexible. Thank you so much, John. And I do want to say thank you very much for the wonderful What's Up presentation. I always enjoy your presentations very much indeed. And anyone saying that I've inspired them to do anything except pull their hair out is just about the nicest thing anybody could ever say. So thank you very much indeed. This talk is one of the riskiest I have ever done, and it is entirely the fault of this organization that I'm doing it. The reason I stepped into this minefield is that some people in the club were asking me, when are you going to do another one of your trips around the galaxy and go visit different star systems? You do that again. You used to do that. Well, I would make up planetary systems for these different stars. And that was great fun for me until they started finding freaking real ones. And over again, they would invalidate the ones I'd made. This happened. And when I was done with production, I'd animated the dumb things like Pollux. Boom, there comes Pollux B, dropped right on top of a planet I'd already made. Ruined it. I had to redo the episode. And over again, literally, I had to move one episode 3 times to go to different star systems trying to run away from people discovering real planets. So I thought, if I'm ever someday going to try to do that again, I better find out what's going on with the whole extrasolar planets thing, the new planets we're finding around other stars, and get a sense of just how bad this situation really is. So I decided to do that. I made this talk. It's only been given one time before, which was at sea to a cruise ship full of people. Their reactions would be very different than yours. And I'll tell you why I'm taking such a risk, especially looking at cosmic debris on my stage left. This audience is notorious for really knowing the subject matter. What a joy it was there on a cruise ship to bring this up and tell people about planets around other suns when a third of them didn't know they had discovered any. It's like, at least just once I've run into a kid who didn't know we landed on the moon. And I got to tell him. And he didn't disbelieve me. He just thought this is the coolest thing he's ever heard in his life. And the people on the ship were like that. And I told them in that room at the time, you just wait till I get back to Orange County and I present this same talk to the Orange County astronomers when they know all about this stuff. And it's going to be tricky because there's so much being discovered so fast in this field now that there is almost a guarantee somebody in the audience has heard something I haven't heard yet. Maybe even literally in the last week or two, there were discoveries where it was coming in so fast. I was adding slides to this talk this morning. Literally, we're going, oh God, I didn't mention that, or this has just come out. It's that exciting a field. That much is going on. This is exciting as it gets in astronomy, as far as I'm concerned, right now. So let's touch base. Let's see a little bit about what's going on with all of these brave new worlds. Long a dream. This is something I've been thinking about for a very long time. When I poked my head around that door in 1984, thinking I'm going to meet girls interested in astronomy, so I came here. Some dreams ended the moment I stuck my head in, saw a bunch of engineers in middle age, but I'm teasing, of course. But at that time, I had books full of imaginary planetary systems around other stars. I'd been doing it since junior high school. I'd been writing these things up, and we knew of not one anywhere. It was the incredibly frustrating thing. But now that has indeed changed. Ancient philosophers and in a historical period philosophers who knew that the sun had the system of planets going around it, whatever else, the system of the universe, obviously wondered if it was the only one for a long time, out sitting on a rock having the philosophical discussion. This was harmless, and nobody would be right and nobody would be wrong. If you imagine maybe there were other worlds out there, it was a theoretical discussion. But even By the time we found out for sure the Copernican revolution, with telescopes, we demonstrated they are all going around the sun, all the rest of this. Please remember, we did not know if this was a unique structure in the universe or if any other examples existed. We did not know. For one thing, we did not even know what stars were. Right? We didn't know what made the sun shine. That's true, our own sun, but we certainly didn't know what made the lights in the sky. There were people who had opinions about this, some of them dead on right, saying, I think those are other suns. Some people did say that, but there was no way to know if it was true. Stars or suns, I was uprated significantly for pinpointing Professor Bissell, who discovered, famously people say, the first successful parallax, Bessel, in, I believe, 1838. However, I was corrected by a Scot who pointed out that the absolutely very first was by this Scotsman, who correctly was able to get a result proving the distance to a star in 1833. The reason this falls into this talk and is important is once we had the distance to the stars, we knew what their true brightness would be, and we were able to calculate that relatively to our sun and indicate it is a similar sort of object. Even if we didn't know what was making stars light up, we knew they were in the sun class of objects. This ignites the fire under the discussion of whether or not they could have worlds going around them by demonstrating that these things probably are other suns. That leap occurred then. And then the hunt was on for a very long time. For incredibly ancient people like me, you might remember Peter Van de Kamp, famous astronomer. That fellow it was like Ahab and the great white whale. He was going to find, and there were reports even back in World War II. There were reports from astronomers looking at wiggles in the motion of stars where they thought the gravity of a planet might be tugging on it. And there were constant announcements of a possible detection if people were waiting on tenterhooks. And remember, we're talking like during World War II. In this example, this is 1963, where he is famously announcing a potential planet. This, I believe, is the Barnard star planet that he was looking at a possibility of. And it turns out in this case and in the others, it was almost always instrumentation problems. The problem with the telescope, the drive, some kind of the error in the measurement of the position of the star. It required a precision that technology couldn't quite pull off yet. So right on the edge of possibility, people looking desperately, trying to find the first definite positive detection. The day did come. Eventually, technology got better and better and better. This is January 9th, 1992. When actually all of us, or many of us, were sitting in this room, including me, we were talking about the exciting new news that they had finally found a planet. And it started weird. I love the fact that when technology allowed us to find some of these planets, the very first ones out of the gate were freaks. There's the millisecond pulsar planets, planets around a star that had already gone through a supernova explosion. This is not supposed to be possible. Any system around such a sun should be absolutely vaporized, eradicated, and yet the planets were there, immediately teaching us that we were naive in our expectations of what would be out there. And the famous 51 Pegasi, the hot Jupiter type planet in close to its star, again, not what we were expecting to see. So these early indications showed us that what's in the universe out there is not only stranger than we suppose, it is stranger than we can suppose. And it's continued on like that beyond, and we have a lot of surprising things to talk about. I'm especially looking forward to talking about the densest and least dense planets out there. You're going to like that one. Slide coming. I don't need to even show you guys this slide. For the folks out on the cruise ship, they didn't know how far away the stars were. They didn't know how far a light year was. This audience, you guys drive that commute every week. Okay, this is familiar territory to you. It's important to indicate, obviously, these stars are so incredibly far away. No, you can't just look and see the planets and all the rest of that. The stars are indeed very, very far away, as you know well. You also know that just taking a picture, even if you are an accomplished observer, is not going to work out well for you because the stars are so incredibly bright. Even the dim stars are incredibly bright compared to the tiny, relatively tiny planets that would be going around them. Stars will often be in the order of 1,000,000 times brighter than any planets they might have. The light from the star completely overwhelms them. That made this most obvious way to detect things look like almost a lost cause. But obviously, especially with space telescopes and sophisticated systems on the ground for blocking out the light of a star, digitally subtracting the light of a star, eventually, yes, they were able to do this. The slide you see there, that is a recent slide on the right, the image of an actual planetary system. Not all of them, the two indicated with arrows, are large super Jovian type planets, bigger than Jupiter, around a young star. We're finding lots of these now, and this is an example of a recent result that's just happened. So it's tricky to do, but yes, this did end up working. Direct imaging, we have actual pictures of them. Astrometry, this is measuring the position of the star, looking for a gravitational tug moving the star around a little bit and inferring the planet. In other words, what Peter Van de Kamp was trying to do. What's the difference? Precision technology is allowing us to measure really small differences in motion. You will see down there, I think, yeah, the declination and right ascension. MAS stands for milli arc seconds. This is a tiny fraction of a single arc second. Remember, the size of the moons of Jupiter in your telescope are, one or maybe 2 arc seconds across. This is a tiny, tiny measurement of change, but it does work. The technique was fine. This is an example of a real detection that was done. Radial velocity has worked and worked well. This is again, the star is being moved around, but you're looking at the light and looking at the spectrum of that light, and you're able to see whether the star is moving towards you or away from you. And of course, on the balance beam between the star and the planet, as the planet goes around, the star also goes around the center of mass between the two of them, and you do get the wobble. That wobble can be detected just looking at the light of the star, and many of the characteristics of the planet, of course, can be inferred. 51 Pegasi, the hot Jupiter I mentioned, you see shown on the right. That is a good example of that technique, and it has worked very, very, very well. There are lots of candidates that have been found that way. Transit has also found a lot. Again, remember, the planets are usually quite small compared to their star. If you are lucky, though, and they are lined up the correct way so that from Earth, the planet will block a little bit of the light as it goes across the face of the star will dim a tiny bit. And you can watch for this. They've done that, especially with the Kepler Space Telescope. The TESS spacecraft also has been doing this a lot, and we have found lots of those. There'll be a slide to show you just how many we're talking about in a moment. This is so complex. Gravitational microlensing, this is not one of those easy things to explain. Imagine me showing this to those poor people on the ship. That's a tough one. You guys, you're going, I know that gravity bends light. It focuses light from distant sources and can make things visible or detectable that otherwise are not. Sure, but for a lot of people, if a normal college student should wander in here, or the people from the Turtle Club right down the hall, if they wandered in and heard me talk about gravitational microlensing, they would run out of here and screaming. But the main thing is this technique also does work, and we have found some extremely distant planets, more on that in a moment, using this technique. It's a very powerful technique. Pulsar timing is another one. That's the one, like the pulsar. Again, this is another technique that can only be used with these rapidly spinning stars, whose behavior is very precise, down to a tiny fraction of a second as they spin and send pulses our way. That allows them to be used very precisely to show any variations in their motion. And yeah, we have found some planets here. Remember, originally we thought there'd be none at all, meaning, sure, it'd be a great trick if there was a planet around a pulsar. You could always use the pulsar. That'd be great, but there won't be any planets around pulsars. Well, surprise, there actually are. All right, what have we found? I love the fact that my father got to see a lot of developments in astronomy, born 1920. By the way, you can imagine he worked on the moon missions. He got to see us walk on the moon, all the rest of that. Got to join the Orange County Astronomers. Those two were our seats for me and Dad sitting here. And when my dad passed in 2005, he did live long enough to know that there were planets around other stars. When he passed in 2005, there were 287 known planets. 287. What an amazing thing for my dad to know there at the end of that cosmic journey that he had been on. Today, the numbers are slightly larger. We have found a few more. Okay, ballpark of 5,500, definitely confirmed. In 4,000 odd star systems, multi-planet systems, 878, these numbers as of Halloween. And candidates, which have been detected but not subject to scrutiny to be absolutely certain they are planets, almost 10,000. Round them all out, we're looking at the ballpark of 15,000 worlds that we have found so far, with the full expectation that we are going to be finding many, 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 many thousands more in the next decade or two. So we have indeed struck crumpet, as the British say. We have definitely found them. They are out there. They are common. They are everywhere. The news is really exciting for you. But for me, trying to find a planet where I can imagine my own planet system for my own planets for my star tour, this is really bad news. The dumb things are everywhere. The planets do indeed line up the way we had many of the daydreams about them, where you would have the small planets, which you see on the left of your screen, down all the way to ballpark of Mars, the solar system's planets shown in orange. We have found a number of planets there. You may see TRAPPIST-1 indicated. The planets in that system are small, apparently rocky planets like the Earth. Yes, meaning Earth is not a freak. We've found lots of planets like that. Going on up, I do want to call your attention to a weird gap. They don't just smoothly populate. This is not all of them. This is a selection of planets. This is a diagram from the Planetary Society from 2019. And here they have the ones we had really good estimates about their mass and their size. So you could plot them on this diagram. There's a gap, not just up to Uranus and Neptune, which are almost in the exact center, but as you start getting bigger and bigger from the Earth, there actually is a zone where there aren't any planets. There aren't as many. There are very few. That's a real gap. That's an example of one of the kinds of things we found where I would never have dreamed of that. It turns out that if you make a planet just a bit bigger than the Earth, they don't seem to be able to hold on to their atmospheres very well. They're not big enough to be a small Neptune yet. If they have that much gravity, yes, they'll stay like that. But there's a zone of instability where you try to make a planet that's, say, 5 times the mass of the Earth and try to give it a big fluffy atmosphere. Over time, it will lose that atmosphere, especially if it's close to its star. So there's actually a gap where those planets, they might have started that way, but they drift off that point and either get smaller and rockier, or if they're far from their star, they'll grab extra stuff and become something more like a Neptune. That's an example, one of many, many surprises. Notice also it's not an absolutely straight organized line. Some of the planets are higher in this diagram. They're raised kind of off the line. Those planets are less dense. They actually are fluffy. Okay. They are bigger for the same mass. And that is one of the things we found. Yeah, there are fluffy planets, and any that are well below the line are denser than the average ones. There are planets that are denser and heavier than anything in our solar system, for example. Again, the slide coming will freak you out. It certainly freaked me out. Wait for that one. How many of the different types? 1,700 gas giants so far from one recent estimates. Then a little bit smaller planets like Neptune, Uranus, about that size, 1,800 odd. So lots of those. A kind of planet we don't have in our system, the super Earth, 1,600 odd of those, meaning bigger than the Earth, 2-3 times the mass of the Earth, a little bit bigger than the Earth. We just don't have one in our system. So it's a little bit of a shock to us. We're provincials. We just didn't know. A lot of systems have these things, and we don't happen to have one locally. So that was interesting. And then terrestrial, getting down into the size of Earth-like planets, getting close to 200. But you notice the numbers lower, but don't despair. That doesn't mean there are fewer of them. There are probably far more terrestrial planets than there are the big gas giant planets. They're harder to find. That's why there are fewer of them in the list. We have to take that into account when we're looking at these. And then unknown, I love that. I'm not even sure what it means. I'm quoting directly from the source here. 5, unknown. I don't know exactly what they mean by that, except that there are some real freaks out there. It's very hard to say. We don't know that much about details on their composition, so maybe they put them in there. Here are the rising numbers of detections as you pile on and pile on and pile on worlds after worlds after worlds to get to the numbers we are now. Notice, by the way, the different techniques. You can see here what worked especially well. In red, radial velocity, measuring the approach and retreat of the star by looking at its spectrum, at its light. That worked very well, but holy cat, look at those transit indications. The green bars, we found huge amounts of these by transit, especially the Kepler Space Telescope. And now we have also got the TESS mission and, of course, also the James Webb Space Telescope. These are capable of doing this. And then you've got on top there a few of those other exotic ones. Imaging, notice, the one we, as kids, would all have thought, oh, they'll just take a picture of it. It's actually very, very few of them are suitable for that. But these other techniques work very well. And as we put up more space telescopes and develop more sophisticated ground systems, there'll be more of that, a lot more. Detection biases. Always remember this for what we're able to find. More massive planets are easier to find, especially for the radio, anything that's measuring the deflection of the star by gravity. If you have a big giant planet, those will be easier to find. Those pulsar planets were a real rabbit out of the hat trick surprise for all of us. They were small. We weren't expecting the first ones we found to be small. 51 Pegasi is a hot Jupiter. That's a big planet, half the mass of Jupiter roughly. And that would be an example where the big planet moves the star more, makes it easier to detect. The same for larger, physically larger. With mass, we're talking, well, weight on the Earth course. But with the size, how would that help you? It'll help you if you're looking for eclipses. The transit method, a bigger planet crossing the face of its star, deeper eclipse. It blocks more of the light, much easier to find. Here, this is really important. Faster orbits. In reading the literature a lot, like even this morning, I was reading scientific papers, they talk about this endlessly. If you've got something that goes around its star once a year, then you've got a shot in, say, 3 years to see it do the thing, whatever it is, wobble the star, cross the star, whatever, 3 times. That's good for science. You've got to see it do it and do it and do it and do it to get an orbit out of it. You would wonder, like Neptune, or okay, it just did it, and in 200 years it will do it again. This doesn't result in a scientific paper, right? You can't do that. Even something like Saturn, you're talking almost 30 years. So this is poison to finding these things. And the scientific papers have to take this into account and acknowledge there are probably lots of the long period orbits that are just, we haven't had enough time to catch it doing it again, or the trend is very, very slow. I think the star is moving. It seems to be moving. Ask me in 5 years. Okay. We're keeping track of these stars, but we got to get back to them if we're going to catch those. Now, for direct imaging, hotter planets, super hot planets, right? They're screaming in the infrared heat. That, if you're doing infrared, thinking of you, James Webb Space Telescope, anybody looking in the infrared, if your planet's hotter, it's much easier to detect. Really cold planets, if you look at the surveys, they're almost missing. There are some, I'll show one. But the thing is, if it's cold, the infrared people can't find it very well. And one good way to be cold is to be far from your star. And if you are far from your star, that means a longer orbit, right? And all those things mitigate against being able to find it easily. So hot is good. That's easy. The star being dimmer or cooler, remember that 1,000,000 to 1 ratio? Well, maybe it's only 10,000 or 100,000 to 1 if your star is just barely ticking over. That's why TESS, the Transiting Extrasolar Planet Survey Satellite, is looking at the smaller stars, the dimmer stars, because it's easier to pull off this trick of finding these things if the signal from the star is less. Okay, that works very well. And wider orbits or closer to us works well only if you're really doing the photography thing to get it farther away from the glare, a bigger orbit, right? That's the one time being far from your star is good, but it'll also help if you're hot out there. If you're cold, it'd be hard to find. Implications: planets in our galaxy, not very many, only about 100 to 400 billion, which means we are going to run out of zip codes. This is going to happen. Habitable planets in the galaxy, George Lucas, take note, about 300 million minimum, meaning something like the size of the Earth and something like in the right distance from its star to have temperatures for liquid water. So yes, lots of those. And a specific number I just put in there this morning, the nearest Earth-sized planet in the habitable zone of just a star very much like ours, all those restrictions should be about 20 light years away, something like that. So right in the neighborhood. And now this was a prediction that was made, but I should point out the discovery of Proxima b, 4.2 light years away, immediately next door, is an Earth-sized planet smack in the middle of the habitable zone, not 20, but 4.2. These are estimates. It could be a lot more planets than that. So lots of opportunity for Starbucks and warfare. I just wanted to show this because I love that this stuff exists. This is from the University of Puerto Rico. They have a habitable planets or extrasolar planets website. And on that, they have the exoplanets orbital catalog. The image you see on the left there, that's a real planet's orbit around its star, the gray shaded area, the habitable zone. This is an example of a wild orbit we don't have in our system, planet G in this system. Notice there are a lot of planets in this system. It's swinging from the inside to the outside of the habitable zone where it would be hotter, where it would be colder. It's not a planet like the Earth. It's a giant planet. An illustration of that type is shown on the right. A water cloud Jovian, which should have very pale colors, maybe pale blue is their estimate on those. But again, they have pages and pages and pages of orbits because you can sit there and toggle through them just system, 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 system. And these orbital diagrams are flashing at you as they go by. And I'm just thinking, this is Star Trek. This is what I was waiting for. And it is like that now. We are getting these kind of catalogs. So as regards a system, my proven system, meaning the one system we had proven was the solar system. Is there anybody as old as I am that remembers Bode's law? Right? Yeah, I remember. Yeah, where the mathematical progression of the distance of the planets in our solar system, it goes way back, right? Where they worked it out that you could add a certain amount and the next orbit should be about here and about here and about here. And they thought because it kind of worked for the planets of our system, we discovered some fundamental blueprint of the way the universe works. And there was even a planet would be made between Mars and Jupiter. And it was right in the middle of the asteroid belt. So everybody's thinking there was a planet there. And it blew up, when the Death Star came in and blew it up or whatever. But really, Bode's law was a big question. So was that going to apply to all these other systems? Was it really a thing or not? We got a lot of systems now. We can look at it, and I'll tell you the answer is no, it is not a thing. Bode's law does not hold sway in distant systems. That's interesting. They are not all the same. These are examples of systems drawn to the same scale. They have all kinds of different orbital architectures, evenly spaced, incredibly clumped in the case of one that I'm thinking of, where two planets are approaching each other almost as closely as the Earth and Moon, darn near, in two orbits that are right on top of each other, and then nothing around them for a huge distance. Completely different kinds of systems. They're arranged all different ways. And again, there are thousands of different architectures. Speaking of architectures, this is one of the ones that was a big bugaboo for me as a kid. I wanted to know how they were arranged. Was our system, which was nice and orderly, and they've named that type, by the way, ordered, which I like. The spacing there is a little bit off here. Sorry about that. It's the second one down. That's the way our system is. You got the star, you have the little planets, they're all in close. You have the big planets, they're all far out. That's properly ordered in the way, God intended solar systems should look, meaning ours. And that's what they thought that would be. They call that design ordered. The one on top is the most common, similar architecture, meaning, and by the way, it doesn't mean small planets or big planets. It can be any kind of planet, but whatever your local flavor is, if you like making gas giants, you get gas giant, gas giant, gas giant, gas giant, gas giant. You may have 4 of them, you may have 6 of them, but they're all very similar planets in the system. You may make small planets like the Earth, and you get a little Earth, 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 and you don't get a big giant planet. They're just basically the same design. These are very common. And there are theories now going back and forth about why that's the most common one. I'll spoil it for you. They think that when you form a star system and there is very little material to work with, there's less gas and dust surrounding the star, a low mass disk that surrounds the star, you tend to get similar architecture with the same type of planet, whether big or small. If you have more mass, or you also have more metals in the star, meaning anything except hydrogen, helium, or stupidity, the heavier elements, any of those other elements, you have more of those, then they branch out into those other types of systems. Ordered, and this is the Holy Grail. This is one of the ones we have not found. We don't have a single authentic, known, definite case of an anti-ordered system. Haven't found a one for sure. Anti-ordered is big guys on the inside, little guys on the outside. However, we had a guy from the test mission come up to Griffith, and I asked him about this, and he said, hold on. Yeah, I know what you're talking about. The computers predict there'll be a lot of those. The computers think you will form the big guys in close. In fact, they think it's a very common type of system, but that would make the signal of little tiny planets. Remember farther out? I warned you about farther out planets. Farther out, smaller planets would be very hard to detect. All those hot Jupiters you're looking at, or warm Jupiters or whatever, where you got a big one on the inside, and today we think it's the only planet, stay tuned. We may later find out there are smaller planets farther away, and it truly is an anti-ordered system, that fourth type of architecture. On the top, shown to the same scale, each of the planets compared to our system, you've got the Kepler 90 system around a star that's very much like the sun. First of all, isn't it cool that we got a map or a drawing like that even exists? It's just all these worlds. I told you about the in-between kind of planets, the super Earths that we don't have in our local system. Look at all those. Kepler 90b, 90c, 90i, 90d, 90e, 90f. All of those are in between Jupiter or between Neptune and Earth's size. Is very common. And then it's got some big gas giant planets, and those are on the outside. It's an ordered system. You're thinking, cool. This is just like home. But there's something missing, which is the size of the orbits. The entire system would fit inside the Earth's orbit. The whole thing. We're talking about these different architectures, but we didn't talk about size of the system. Remember that, what was it, Men in Black, where they had the galaxy that was in the collar hanging on the dog or something like that? This kind of feels like that. Yeah, we got a solar system. It's here on the table somewhere. Hold on. This is a tiny solar system. And the fellow who came to talk to us from TESS said this is one of the common things. They said about 1 in 3 of the sun-like stars that has multiple planets has a tiny system in relatively close. That may be kind of bad news for worlds like the Earth, because getting in really close means they're going to be hot, okay? But we didn't know that many solar systems exist, and there are quite a few. They're not always small stars. They could be a star just like the sun and have many planets. We don't know why yet. The TRAPPIST-1 system, famous around that little red dwarf star. You see it there at the top. Architecture type, similar. It's bit large, on the order of the size of the Earth. They got Earth, a whole bunch of those types of planets in the same system. And as you can see from the inset, they would all drop way inside the orbit of Mercury. That's a good thing, though, when the local sun is a small one, a dim one, and this one is. So you've got that green zone, planets E, F, and G, in that tiny system are at about the right distance to be the habitable conditions where you might have liquid water. Of course, it's also very close to the star, so stellar flares and things like this could even strip away their atmospheres. And latest news from the TRAPPIST-1 system, they are finding indications that these planets do not have atmospheres at all, that they have been stripped naked by their star. So again, well, you know, we're getting street smarts, the very beginning of street smarts in our galaxy. Don't go in close to one of those red dwarfs. You're not going to find anything. A lot of them will have their surfaces bare, like the moon, even though they're the size of the Earth, just bare to space. That's not for sure in this case. They're still looking at the system, but there are preliminary indications. I thought this was cute. I just put this out here out of sheer confessional. They have supercomputers that predict what kinds of systems are out there. The simulation now says 80% of the star system should be the similar types. Observations that we have, yeah, a lot of them, 60% is what we've seen. Ordered like our system, computer, Hal there seems to think it's only going to be 1.5%. But it's 37% that we found. So maybe we're not so freakish after all, and the computer's a little wrong. Again, anti-ordered computer expected 8%. Anti-ordered so far, 0 found. Mixed, 8% from the computer prediction, 5% as far as what we've found. This is a diagram that I put in here literally this morning from the same paper where they were doing the computer modeling. These are not the computer models that it was kicking out. These are all real systems. If you look in the left-hand illustration, you'll see most of the way down, sun is indicated. Our system is indicated. These are at the same left to right scale. Bigger planets are drawn bigger on a scale that's not quite physical, but if it's a big dot, it's a big planet. And you can see in our system, we got the 4 little guys, and then we got the other ones on the outside. All the systems in that white area of the diagram on the left are considered to be ordered. A few are found to be mixed. The other side on the right is that thing continuing down into its next section. All the similar systems, similar. And notice some of those are big giant planets, which are all the same type in the same system. So this is just a zoo to look at of solar system types. Ours is not freakish. It's not totally weird, but there are variations. Some inferences. I mentioned that the similar star system should come from low mass protoplanetary disks. If you don't put many ingredients in the oven, you're probably going to get same type of planets for all of them. This is an interesting distinction. Nature controls just the basic ingredients when you start. Like I said, if you have a lot in a lot of ingredients, you're probably going to get similar. If you have if you don't have many ingredients, you'll get similar. But if you have a lot, it'll be one of the others. But what happens to make it one of the others? This may be our story locally. Interactions between the planets. If you've got a lot of stuff, you could end up as a mixed system with scrambled planets. You could end up as an ordered system, little guys in, big guys out. You could end up as anti-order, big guys in, little guys out. It all comes down to the history of our system, and we have suspicions that exciting things may have happened in the very early stages of our solar system's development, with, for example, Uranus and Neptune probably changing places in their orbits, with Jupiter probably having scooted in, certainly with the Earth getting whacked by the Theia proposed planet to make the moon. Exciting things happened in our own system. Is that what changed us into being an ordered system? Maybe the type of interactions we had locally compared to one that ended up the other way around, anti-ordered. We're in the infancy of understanding any of this, but we're getting clues now that if you look at an ordered system like ours 1,000 years from now, you'd shake your head and go, I know what happened there. I know what happened. A nearby star passed close to the planets when they were forming, or whatever, who knows. The last thing I mentioned, increasing dynamical interactions tend to evolve systems from being one way to another way to another way. They'll actually swap. They'll change. Now, I'm not saying Jupiter was ever on the inside. Okay, I'm not quite that crazy, but what if we found out that was the truth? What if the Earth started out as a snowball at 5 or 10 AU? Our system got passed close by a massive star. The local system freaked out, ejected the giant planets, and somehow the small planets ended close to the star. I'm not suggesting that's a pretty wild scenario, but that's the kind of stuff we're talking about here. We're just starting to learn about it. Hot Jupiters. There's a painting some hack space artist did many years ago. You remember that? It was such a rude shock for everybody when we found it. Going, oh, they're all going to be like that. We found this thing, and now all the Jupiters, they're going to be close to their star, which means they had to form far from the star, wander in. If they did, they're going to scatter. All the planets that aren't going to be. It's like a kid freaking out at Christmas or something, thinking everything's ruined, right? All the planets are going to be ejected from all the stars everywhere because we found these hot Jupiters, and we're finding a lot of these hot Jupiters because they're massive and they're close to their stars. That's why we were finding a lot of them. I told you it's the easiest kind to find. Of course, they were first. Don't freak out. It's okay. The estimate is now for stars like our sun, the G-type star, the 1 in 182 of these will have a hot Jupiter in it. They're not that common. This doesn't happen all the time. There are lots of different types of systems, as I showed you. It was just that we found these first. So don't worry about that. Here's something I did not know. I did not know there was a difference in, because there are a lot of stars they talk about, but like half of them are multiple or binary stars. They talk about that. I didn't know there was a variation by type. Did anybody else know that one? Apparently, I'm the last guy to find out. And I found out, I'm not kidding you, this morning. I found out this morning. And I threw this slide in there going, why didn't they tell me in 1984? I wouldn't have looked like a fool all these years. The O and B type stars, the big bright blue ones, on this diagram, they're saying north of 75 to 80% of them have a companion star. I can name some. I got it. I just didn't know this. For stars like the sun, yeah, it's about half have a companion like that. And I certainly didn't know for the little red and orange guys, they actually have fewer companion stars. I had no idea. I read it in a paper. It must be true. Tentatively, right? At least it is reported. Now, but if this is the case, and lots of these have multiple stars out there, can you have planets? It would be tricky. This shows the types of orbits a planet might have in these scenarios. S-type planets orbit one of the stars. It's got one local master, serves that star, goes around that star, but there's another star in the system. Both of them could have their own planets. They talk about that for Alpha Centauri. The stars are far enough apart, they might each have their own planet system, each one respecting one star. Now, P-type planets are the ones I really wanted after May 25th, 1977. That's the planet I wanted. With the double sunset, it goes around a pair of stars, a circumbinary planet. But come on, that's a lot to ask for. The gravitational forces are going to be messing with any planet there. Besides, the second star formed in there and it probably stole all the ingredients. There's probably nothing left over to make a planet. So, of course, they can't have any. Well, it turns out they happen. It turns out we found them. And there is a area of instability. You guys know I've really gotten into the science thing now that I'm showing charts, right? It's like very serious looking, and I even wore a coat, all right? So this is real. This diagram here has the dashed lines running across it. The basic idea is if the stars are far apart, yeah, that'll work. You can have a circumstellar going around one star as all the ones in the lower right are. That's fine. We've found lots of those. But then there's an awkward zone where the stars are getting closer together and their gravity is affecting you more and more and more. And then it would tend to steal a planet around the other star. It'd throw it out. You couldn't have a stable orbit. You would eventually get perturbed out of your orbit. It makes a zone of instability. But if you are far enough away from a pair of stars, at a certain distance, you can go around both of them safely, meaning Tatooine, Star Wars. You can do it if you keep a certain distance, and they have found some. As of a number of years ago, it was about 20 that they found. So they definitely do really happen. Here's an example, Kepler 47. There are two suns in the center of that diagram. It's got two gas giant worlds known going around it. Just one example of a number of these types of planets we have found. It actually will work. It exists in nature. Okay, extremes, street smarts. What have we found that's crazy? What have we found that's nuts? This is a pulsar planet. Again, some hack space artists rendered this view. I don't believe any ones that I do. It really kills me when I look at a NASA thing and I know some guy who's just about as smart as I am did the artwork for it. I don't buy anything anymore. This is purely an estimate of what something like that might look like. So yeah, that's one example, a planet around a pulsar. It's extreme, but it is definitely out there. Here we go into some comparison. Most massive, least massive. We have found planets like HR 2562b there, which are about as big as a planet can be and not be a star. They go all the way up to that border and across it, off into the brown dwarfs, off into the red dwarf stars. They get as big as they can. No surprises there. There's no top end to planets before you get to stars. It's not like planets get up to a certain size and then way short of the stars knock it off and don't get bigger. No, they get, there's a grayscale all the way up. Okay. And that's an example there of one of the big ones. Now, Draugr there, yes, its proper name, a real name, love the Norse name, Draugr, is one of the pulsar planets, not shown accurately in scale to the other one because it wouldn't show in the diagram. It would be a tiny speck. Its mass is 0.02 Earths. To give you a sense of scale, the moon is a little bit more than 0.1 Earths, so or 0.01 Earths. So this is a ballpark of twice as massive as Earth's moon. In terms of mass, we are indeed finding some very small planets. And we can confidently expect they go down from that to past detection under any circumstances, down to asteroids, down to comets, to Nutter Butter peanut butter sandwich cookies. They go all the way down in size. But so far, Draugr holds the record for smallest. Now, or at least massive, For smallest, these are biggest and smallest. Our current ones, the very young Proplet 133 353b in the Orion Nebula, orbiting Theta, is it Theta C Orionis? But it's in the trapezium cluster. A very hot protoplanet baby is considered to be only 88 times the mass of the Earth, but it is apparently 8 times the size of Jupiter. It is almost as big as our sun. It's, Jupiter, this thing. And it's not even as heavy as Jupiter. That's freaky. Well, how can that be? Well, it hasn't settled down yet. It's recently formed. It's gaseous. It's very hot. It's very puffy. Those are the conditions can get you a planet of that stupid size. There are many examples of planets known that are 2 and 3 times the size of Jupiter. For physically small, that name I'm not going to give you. Boy, they got these romantic names down, don't they? This size of that one, 0.0101 Earths, this is an object which Earth's moon is 0.27. This thing is on the order of an asteroid. This is very physically small, orbiting a white dwarf star, which is itself very interesting. Densest and least dense. I promised you this one. Just take a moment and come on the journey with me, because sometimes the NASA sites, they list this and it gets really weird. Please remember, ladies and gentlemen, Saturn is 0.687, famously will float in water, right? You guys know that trick. They always tell you, 1 is the density of water, and this is 60% of that and would float. Lead is 11.34. The Kepler 131c, screen left, estimated density 22 to 132. Lead is 11.34. Even the low number freaks me out. What do you mean it's twice as dense as lead? That's incredible. And they've got a size for it. They've got a mass and an estimated diameter. If those numbers are right, it's got to be highly compressed. That's the only answer. For physical matter, this is about as dense as you get. It's got to be crushed in by the local gravity, which would be very, very strong. And if it's 132 grams per cubic centimeter and lead is 11, I don't know what that thing is made of. It's very incredible. Looking the other way around, over on Kepler 51c, that density It's not 0.6, it's 0.034, meaning that planet is so fluffy. They even have that designation, super fluffies, I think they call them. I'm not kidding. That planet is less dense than styrofoam. Yeah, what the hey? But that's the fun of poking around in the galaxy and getting these kind of numbers. It's a planet made of styrofoam. The simple answer is it's fairly hot, fairly. So it has puffed up a bit. That may be part of it. But some of these are really fluffy and they don't think the temperatures are that high. So we don't have that excuse. There's something out there that makes fluffy planets. And the answer is nobody on God's green earth knows why yet. I just think that is amazing, and I'm still trying to wrap my head around it. Surface gravity, some of our same usual suspects here. I said the surface gravity would be high. Surface gravity 11.86 G for Kepler 131. That's if the low number for its density is true. It gets much worse if it's higher. Jupiter is 2.5 and is the worst gravity in the local system. And this is 11. So, wow, that's incredible. And for the styrofoam planet, it is like 8 times the diameter of the Earth, and the gravity is much less, like a third of Earth's moon. Wow, freaky stuff. Hottest and coldest? Hottest, as hot as you like. Depends how close you are to the local sun. Is 7,800 Fahrenheit sound okay? At this point, you're luminous. You're glowing. There are plenty of planets like that, and Kelt 9b is an example. The other way around, minus 364 Fahrenheit, we're pushing down into close to absolute zero type territory for the star or the planet there shown with the unpronounceable name. Youngest and oldest, youngest, all the way bottom of the scale. It's listed as younger than 500,000 years. The truth is it's being formed right now. It's not done yet. It hasn't rolled off the lot. It hasn't lost value yet. This planet has the new planet smell. It is still being constructed. So how old is a planet that isn't done yet? Okay, so they're as young as you like. And if for old, now we don't, this is one of the pulsar planets on the other side. Again, not shown to scale. These are just very small planets. Because it is in the cluster M4, the globular cluster M4, we believe it, star is a member of that. Based on our understanding of the age of the cluster, it make it 12.7 billion years. For those who knew the age of the Milky Way galaxy, this gets very interesting. This is a world that was born alongside our galaxy or even before our galaxy really took shape. In fact, scientists have said they think this planet is so old, it may have probably changed suns in the past. There are dynamic histories they've been able to calculate for this thing because of the density of stars in a globular star cluster. It's quite possible it isn't even orbiting the star it formed around. After 12.7 billion years, you get to do whatever you want. That's very impressive. Closest and farthest in the universe. Closest, the immediate closest star in the entire universe. 4.2 light years, sitting there right in your face, as close as they can get. And in our galaxy, the farthest so far to date, out by the core, all the way at the galactic core, 27,000 odd light years. The asterisk is there to say, yes, but hold on. You have the suspicion there may be some farther out in the universe. Oh, yeah. Oh, yeah. The ground's about to drop out from underneath you. Exoplanets, ladies and gentlemen, a brand new word. Exoplanets has been coined as the term to describe planets not outside our solar system, but outside our galaxy. Using things like gravitational lensing, they have indications definitely detected, although not repeatable, so they can't get really good data on these. They're sure these planets are out there, though. Sure, 2.5 million light years in the Andromeda galaxy. They found one. And then M51 out there in Canis Venatici, 32 million light years. That's how crazy this is getting. And of course, you know they're going to find them farther away. They're in all the galaxies. They're everywhere. But you don't care about all these freaking snowballs and balls of molten lead and fire and death and doom. You want a place like home. I understand that. Well, hold on. We don't know that much about these planets yet. We know some things like the mass, the radius, depending on how you detected it, surface gravity. If you've got the mass and you've got the size, you can work out the surface G. The orbit, yeah, pretty good idea on that. The stellar flux, meaning the amount of sunshine it gets, yeah, you can work that out pretty easily. And the yellow zone in the middle, we're starting now to get information on atmospheres. Albedo, meaning the true brightness, how much sunshine it reflects, that's very important for temperature. And then temperature, yes, they're getting some data on that. But a lot of things we don't know, like the actual true age. We have estimates, like in the case of that really old one. It's the star that it's in, the star cluster it's in, we're guessing. The rotation of the planet day and night. We don't know about that. The inside of the planet, we don't know about that. The surface history, nope, we don't know. And of course, life, no, we don't know. You remember that? The professor was in here before. You remember you would talk with him? What was the first question he asked me? It's like, are you going to talk about life? I just did. We don't know. Here's a slide from the James Webb Space Telescope. Spectra beginning to come in, finding planets with things, water vapor in the atmosphere. Yes, we're finding some of those kinds of things. We are detecting the beginnings of planets whose type we have imagined water-rich worlds with very deep water oceans, but no solid surface, and so forth. A number of the types of planets we're finding are what we're expecting. But as in the case of those TRAPPIST planets, in some cases, we're getting results suggesting no atmospheres or atmospheres of types that we were not expecting. This is an infant science, and the James Webb is one of the few that can help us with that. More information will be coming. For looking for an Earth, this is a plot of Earth similarity from the Puerto Rico University Planetary Habitability Laboratory. The blue spot is the sweet spot. These planets marked with black dots on different axes of how big they are, top to bottom, and then how much sunshine they get left to right. They're looking to see, is anybody about the right size, getting about the right amount of sunshine? They actually give them a number for how similar to the Earth they are, an ESI number, Earth Similarity Index number, and they rate them, okay? And as you can see, some of them are getting in the bluish zone. They're possibilities. They have them on their website. You can check them out. These are artists' interpretations, and you know me, you know never to believe artists. That's a good example of some of the planets that are possibilities. The number of habitable planets, there will be very few of them in the galaxy because of all the conditions required. About half of all the sun-like stars have a rocky planet in the habitable zone, ballpark a half, but that doesn't mean it isn't a Venus, okay? You could have the wrong kind of atmosphere, and then it wouldn't be Earth-like at all. The estimate that you're given there, the conditions for that are listed below, but about half of all the stars like our sun will have an Earth-like sized planet in the zone. We'll see how habitable they really are. So now in the parade of worlds, we have Sol F, which is what I'm calling Earth. I love all the numbers. Isn't this a miracle? Mass of 1, radius of 1. Wow. Orbit 1 year. What are the odds of that? How did that happen? So of course we make ourselves wonder. The important thing to notice is that the temperature, if we didn't know about the Earth's atmosphere, we would say the local temperature is -3 Fahrenheit for the Earth. That's the Earth's effective temperature if it had no atmosphere. The atmosphere makes the big difference, raises that to 59 Fahrenheit. So you're going to see some other worlds here. Take the numbers for temperature with a grain of salt. We don't know about their atmospheres yet. Kepler 186f, this is an illustration I did. This is an example of one that gets an ESI of 0.61. It is bigger than the Earth, notice, 1.7 times the size, or 1.7 times the mass, 1.17 times the radius. Temperature minus 78 Fahrenheit. Oh, wow. I don't know about that. That's not Club Med. That's no good. But remember what I told you about the atmospheres. This thing has a thick atmosphere. You can raise that number anywhere you want. It could be 500 degrees Fahrenheit under the clouds. Remember Venus. So, given its size, given the age of its star, 4 billion years in this case, given the amount of metals in the star, it could be made of the right stuff. This could be it. Hey, they're building houses all over the place these days. Maybe this is the next spot to alleviate our housing crisis. Here's another one in the Gliese 667 system. Earth Similarity Index, 0.76, a little bit higher. Younger system, 2 billion years plus, but that's a chunky planet. Look at that. More than 2.5 times the mass of the Earth. However, temperature, remember we were at like minus 13 or something Fahrenheit. This is minus 11. It's just about like home. Give it a good atmosphere, fix it up, some curtains, a little paint. This could work. Ross 128b is another sweetheart. ESI of 0.86. In this case, a little bigger than the Earth and so forth. The real problem is the temperature, 111 Fahrenheit. That's kind of bad. But if you like hot tubs, maybe this is the spot for you. TRAPPIST 1D, another one that's a possibility, ESI of 0.91. So they're finding lots of these that are possibilities. Teegarden star B gets an ESI of 0.95. And there are plenty more. Looking at illustrations done by other people, the planet being evaporated by its sun right now, it's not our problem. It's not our planet. But that's an example of a crazy one. It's named Osiris. Love the name. For moons, if you like moons, this is a gas giant planet. It's 8,000 light years, though, so commuting may be a factor. The moon, though, that they think they may have found one of only 2 or 3 possible detections of an exomoon is the moon is apparently the size of Neptune. So maybe gigantic moons really can happen. This is controversial. We're not sure about this guy yet. Example of a brown dwarf. Got those locally in the Epsilon Indi system, right on the edge of being a star itself, a planet so big it glows. Binary, circumbinary planet, Kepler 16b. Very pretty. Enai-Posha, they're giving them names these days. This is the real name. I believe that is a Thai name. Temperature 536 Fahrenheit. Yikes, that's a nasty one. Harriot, one of my favorites, local gas giant, right here close by at 55 Cancri, only 41 light years away. It's in the habitable zone, even though it's a gas giant planet. So that means if the big moons can form, if you look very closely at this planet and its moon, done by some hack space artist, I will tell you that that is a ocean on that moon. Not impossible. And then there's this weirdo that causes all of our problems. The main thing is these days we found so many, we can put the Earth in the parade where it belongs alongside all these others. There are lots of things we don't know. I've mentioned like atmospheres. We're starting to learn about atmospheres, the insides of the planets, the surfaces, their histories, what happened in the local system, moons and rings. We're just starting to find out about the possibilities there. And of course, we don't know about life. Exomoons, notice this is from Lucasfilm. So this slide comes with a caveat. Please don't sue me. I'm not worth your time. But of course, this is the moon Yavin, or the 4th moon of the planet Yavin from Star Wars. We always dreamed whether or not these things could happen. For those of you who want to rely on our local system for all of your wisdom, I will tell you that Jupiter's Galilean satellites are 4,817 times smaller in mass than their planet. And Saturn's big moon Titan is 4,229 times smaller than its mother planet. And if that rule applies in other systems, you might think there's no way you could have a habitable moon. You couldn't make one that's big enough. Those moons aren't big enough. You forget they make gas giants in different sizes too. What if your gas giant is 2XL, right? Or what if it is Upsilon Andromedae D, which is 10.25 times the size of Jupiter in mass? Scale the moons up. How big would they be? Same moons, just scaled. It means that, look at Upsilon Ganymede, which I'm calling it, is 0.25 times the mass of the Earth. Mars is 0.107. It would be larger than Mars at that point. And you can see also, actually, get that out of the way. Going for the, actually, I'll cheat and show you the next slide here. Super Ganymede, 0.256 times the mass of the Earth. If it was the same density of the materials of the Earth, local surface gravity would be 63% of the Earth's surface. That's if the scaling rule works. And for a super Titan around Upsilon Andromedae D, if it worked out, hey, local gravity, 0.91. That big Jupiter-type planet would have no trouble forming a moon of the size to be anything you wanted it to be. And then remember that weird planet I showed you that might have a moon the size of Neptune. So super moons, big moons around these planets are possible. Atmospheres, we don't know yet. Here's a magnificent picture by Damian Peach of Neptune and Triton. In our lifetimes, probably very, very close to the end of mine, maybe easier for some of you to reach, we will probably begin to really get a good idea about the clouds and things like this in these atmospheres. I hope so. The surfaces, no, not during our time. But OCA will go on for 300-400 years, I'm sure, and Charlie will still be the treasurer. And Charlie, at that time, will be very glad to find out the surfaces of these planets because, like these views in our solar system, they'll tell the history and the story of these planets, whether they're active and whether they have diamonds or whatever we need to know. There are lots of spacecraft that are on the job now and observatories around the world. These are just a few examples. And added to that, we also have a whole bunch of new things coming up, including the Nancy Grace Roman telescope. The Plato Space Telescope will be important, and they're developing new technologies all the time. So the data is just going to get better and better and better. We're not going to be getting out to these places anytime soon, despite some very well-intended things to fire giant lasers on the ground to propel microchip-sized little tiny probes to Proxima Centauri. I don't have my hopes up. I've been wrong before. We found lots of these planets, but breakthrough starshot, I think, is a long shot. And as for humans, well, that's why they need space artists, okay? We'll handle that for quite some time yet. We'll have to explore them from here. I'll leave you with this picture here, which is when I first walked into this room, this was my daydream. This is what I imagined might happen. And it was a long shot. It was one I had to shrug and admit, it's probably not possible, right? And yet all of the stuff we've discovered here is really, really exciting. This is a glorious time to be interested in amateur astronomy. Even if we can't see these things directly, we can look at the stars and know many of them now. Stars you can look at yourself and know there are worlds going around them. This is a wonderful, wonderful adventure, and I am glad to share in its opening days with you. With that, I will thank you for your time and attention. If you have any questions, I'll be happy to take them. Thank you. Uh-oh. This is where the punishment begins. All right, John. Okay. Yes, is lunar synchronous.
It's only looking for one moon at any time. And it's not going to see things with longer periods. So you're selecting the small systems in the disproportionate number.
Yeah, and let me read that back for the folks at home. I will say, John is correctly noting that the tiny solar systems is a selection effect that is produced, like in the case of the TESS spacecraft, that have limited times they can observe. They will find the systems with small orbits disproportionately. And in fact, well, they may be completely prohibited from finding things with longer orbits. So it could be a limit to the observation time of the particular spacecraft or instrument, or it could be the length of the grant. I think we're going to find a lot of orbits are determined by the lengths of grants. I'm sorry, did you have any, just one other thing? Go ahead. Ooh, all right. Oh, yes, resonances. Oh, glorious. I understand. Now, this is a pre-publication thing. So I'll change the names to protect the innocent. But the work that you're doing there is talking about a result where you have planets that are in synchronization of their orbital periods. I can, without fear of revealing any of your information before it's ready, say just recently did you see the result for the synchronous orbits in a system where every one of the detected planets is in a resonance. The whole system is like a tuning fork where you've got this one goes around 3 times for every 2 times this one goes, and this one goes exactly 2 times for every 1 time this one goes. And the whole system is like 6 planets, and they're all in resonant orbits. And the reason this is interesting is that, again, these computers, when they're estimating how baby systems are when they first form, they think that most systems form in resonance. And a young system will have that until you screw it up, right? And so they're talking about our past, our history here. We're not synchronized quite that way, although, of course, we have the inner system where you've got some synchronicity involving, Mercury and so forth. But the thing is, our system may have had a traumatic childhood. And that may be one of the things we're going to learn is like an adult or something like the reason we're screwed up is our childhood was terrible, right? Threw us out of resonance. Maybe we'll see. Any other tough questions? Yes. Oh my. This is exactly what I expected, meaning a question I don't have data on. But I will say, talking about Mike Brown, the hunt for, the 9th planet, a true 9th planet, not Pluto, a large planet on the edge of our system, proposed based on the scattering of orbits of small objects at the periphery of the system. I have heard nothing new on that. So obviously, yeah, it would be fun if I was sitting on a 9, Planet X reveal, and I just didn't want to redo that yet because we're not at a commercial break. But no, I don't know. However, that's a good example where it kind of feels like the great white whale story in a way where they're chasing it for a long, long time and the results keep coming up negative. And after a while, they kind of get to be, we don't think of them quite as a kook, but we chuckle a little bit. Oh yeah, Planet 9, there we go again, until they find it. And then suddenly, they're the big hero, and it was obvious that it was meant to be discovered. I don't know if we've got something out there on the edge of our system. Oh, I will say though, apropos list talk, we have found planets at tremendous distances from their stars, much farther out than we have any in our system. So a planet at 100 AU or a planet at 1,000 times the Earth's sun distance in AU is a possibility based on the examples we have seen. It might make a Planet 9 more reasonable based on the orbits we see elsewhere. So that's the one thing I'd say apropos of that. Oh, yes. Yes, sir. Yeah. Ah, that you're asking the wise question, and you'll notice when I like that one planet with the might be 2200 grams per cubic centimeter, might be 132. What's going on there? Error bars, my friends. That's where all astronomers go to drink. Is at the error bar. And it is, yes, there are significant plus and minuses. However, in some cases, especially times where you've got resonances between planets, you have multiple detections, they will refine the data from the other planet back and forth, and the numbers can get quite small after a while. With a number of the planets that I've shown you, if I say that it has a diameter 8 times the Earth, it's probably 8 times plus or minus 0.1 or point, 0.05 or something like that. Not bad, but there is error, uncertainty in all of these measurements. Absolutely, you're right. There is. And you could look at these websites. You'd really have to look at the papers to get the real numbers because it does vary. Any of the top ones? Oh, yes.
Chris,
Yes.
can we have someone from online questions when you
Oh,
answer the?
Of course. Have you got something from me from the distant universe there?
Yes. So the question is, are we looking for planets around black holes?
Oh, now, hold on. I would say yes, in a sense. Of course, we're not expecting them to be around black holes, but that's a story you've heard before. We weren't expecting there to be any. It would be difficult to find them, but gravitational lensing is a possibility in these scenarios. I don't know of anyone who is specifically looking for one. I haven't heard a story yet from anyone who says that they may have found one. But if there's anything in the tale that I just told, it is us constantly getting surprised. Stars near black holes, yeah, there's going to be gravitational disruption, planets flung out of their orbits. And if they're near a black hole, they're not leaving, are they? So I think it's quite possible that they're there, but I'm not aware of a targeted search. Not yet. Do we have some more questions there, Reza?
Nothing yet.
Oh, okay. I'd like to say I don't want to ignore the more distant universe. Oh, John again? Yes. Well, now, yeah, John was suggesting here, what could a planet around a black hole eclipse? How would it betray itself? And I think one of your best bets, if I had to guess, is that you could get some kind of gravitational lensing effect from a planet if you were closely studying the gravitational lensing that the black hole was doing on a more distant source. And you might get a secondary blip in the signature of the black hole, suggesting the presence of a planetary mass. It wouldn't be obvious that it's that. It really could be peanut butter sandwiches or a gas cloud or something like that as well. I don't think it's impossible to find them. It wouldn't be visual, that's for sure. But yeah, a black hole is a huge mass. There's no reason something like a planet couldn't orbit it and maybe stably if far enough out, right? For a long period of time. Stars do it. In fact, actually, we do know stars orbit black holes. We've seen that, especially Sagittarius A star. It's got a whole fan club. It's got more stars going around it than Taylor Swift. And at that point, all those stars, a lot of them, they're going to have their own planets. Then they could eventually lose them to the black hole. Yeah, Doug.
if Light Combo had viewed, tried to view Pluto several hundred years earlier, the same equipment wouldn't have seen it. That the orbit of Pluto is so eccentric and so long that we only get to study Pluto for a short while before it disappears. That being said, Pluto, as we're supposing, not unusual, but there may be much more out there than we possibly imagine. Just too far to see because they have low surface brightness, including the planet X.
Sure.
But if you reflect on it, it's a very spot. They've been doing this for 100 years.
Yeah.
And it's amazing what we've discovered. Such a short tiny little micro spot.
Yeah, Doug was just reflecting on how much we've discovered in such a short period of time. And a lot of these things, if we tried to observe them earlier, we couldn't. And I'm glad I gave you an example at that. The Peter Van de Kamp great white whale chasing the Barnard star planet is a good example where he just knows that there are planets out there. He was sure of it in the way I was. I drew pictures in junior high school. He at least was out looking. He was trying, but the instrumentation wasn't quite there yet. What a maddening thing that must have been for him. But then now suddenly we break through into the clear like we have here. As little as we know, think about how much we know and how fast it's coming. Really fast. The one thing we have to dread as an organization, speaking to OCA now, is they're going to find life, good indication of life. And this lecture hall is going to be crammed with people. We're talking normal people who don't have model railroads. And they're going to be bombing us with questions. And, we're going to have crystal power to deal with. And they talk to their goldfish and who knows what. We'll just have to cope with that as best we can and share the excitement as we all go along on the ride. We're learning stuff at a frantic pace. And it's a little dizzying. The fellow we had out from TESS who came out to the observatory, I remember he said, when I asked him about one of these things, I got to ask somebody else a question for a change. And he said, I don't know. He said, it's all happening so fast, but isn't it fun? I said, yeah, it is. I wouldn't want to study something where so much was known, but a tiny little refinement would come out every once in a while. Henry VIII, yeah, he shaved his beard once. Now I'm looking for something a little bit bigger than that, right? And here, the world's getting turned upside down. We're finding new worlds. Oh, he gave an estimate. He said, I think we're finding a new world about 3 per week now. That's a time I can afford to live in. Yeah, the Rubin telescope is coming. Yep. Yeah, well, yeah. But, everything's been changed. My God, Hubble changed astronomy over and over and over and over again. It's getting changed like crazy. I almost envy the people in the Turtle Club sometimes, but one of these days they're going to show up here. They're going to come down here. The guy in astronomy, I was talking about the turtle people, but not much changes in the Turtle Club. Here, things, maybe I'm wrong, okay, but it seems to me that's the case, that we have an especially exciting hobby and interest.
Chris, we have some questions.
Yes, please. It's probably the turtle people.
Sure. So a person wants to know what properties would the best planet have that you hope could exist, real or imaginary, and not necessarily one we would have to live on?
Oh, yeah. The best properties for a planet would be unlimited free parking, a rectilinear street grid, and left turn arrows. I'm sorry, I work in Los Angeles. You must excuse me. No, there are a number of things. And in fact, the Earth Similarity Index, you notice it went to 1. We only went that far. We assumed Earth is, it's perfect, right? Of course it's perfect. It's Earth. Well, hold on. Some biologists have come up with theoretical ideas about like the density of the atmosphere. Maybe having a slightly denser atmosphere would be better for radiation protection. It would more uniformly distribute heat around the planet. You could have more liquid water on the surface than the Earth has, meaning your ESI number isn't 1, it's 1.5. There are possibilities for life, even life as we know it, where conditions could be better than the Earth. And talk about humbling. That's really humbling. We've always presumed we were perfect. Certainly for us, we assumed we were as good as we could be. If that's not true, if there are the better possibilities, places you'd rather be, I don't know, is that depressing? If there was such a place and there's someplace better and none of us can get to it? Maybe we don't need to know. Maybe that would be sad. I'm not sure.
There's also another question. So one of the messages of your talk is that the fact is stranger than fiction. So do discovered exoplanet findings inspired any new space art scenes?
Absolutely. And I just want to say it is professionally thrilling to have amazing discoveries coming out of epic, perspective-changing new facts, which cannot be clearly seen. Thank you. Thank you. Because that's what space artists call job security. We are the ones right now to show you that, which is good and bad, of course, because we have so much leeway because we don't know how the surfing conditions on TRAPPIST-1D really are. We make stuff up. We have to. We don't know anymore. So yes, all the time I'm finding things that are really inspiring, and I'm trying to keep up. And space artists, not just me, people all over the world are being overwhelmed constantly by chasing after this, like ambulance chasers. We find a new discovery and frantically go to our computers and illustrating boards and try to imagine this into artwork. So it's going to keep me very busy, and science fiction writers, filmmakers, and all the rest. Absolutely. Yes, sir. Yeah, actually, I do. A number of the pieces, well, actually, the image you're looking at right now on the screen, in fact, is one of mine. I made a random planet generator because I was going to show so many planets in that particular slide. Every one of them is separate, and I made a computer program to change color and noise, cloud cover, craters, a whole bunch of things in an animation that would knock out 30 planets per second. And I let it roll all day, and I made, I think, 5,000 planets to cut out and individually drop in there because I couldn't paint that many. That's one example. But yeah, when we're looking at many of the different planets in this, those were my computer illustrations, and at least one of the old style paintings that I did was in here. Extrasolar planets has been a regular part of my work, and always will be until we get there. And then, they'll have real pictures. They won't need me for that. Oh, thank you. Yes, sir. Artificial intelligence as applied to world generation. Yeah. Yeah. Oh, and for discovery, absolutely. One of the things that's not, horrifyingly terrifying about AI can learn from observing data and spot patterns. Like, for example, transits, eclipses, things like this. You could, and they do, obviously have machine learning to go through huge amounts of data to look at that, to find patterns that reveal things like an unusual circumstance, to flag it for a human, to look at that. That's in the scientific world. It's funny that, again, I'm worried about my own job here. My first reaction when I heard you ask that was the people that are using AI to create space art of alien planets. And let me tell you, brother, AI is really busy doing that these days. It's pretty stuff, but at the same time, not a lot of thought goes into it. So I worry about that. I really do. Well, the artificial stupidity part of I don't want to tell our robot overlords that they're stupid. They might be angered. Uh, oh, don't bring Wyland into this. Do any other questions there from the online audience?
No, that was
Okay.
it for the online so far.
Okay. Well, I think. Oh, all right. Hold on. Yes, we have one here. Yeah. Exist. We talk about carbon-based life, which is the only one that we can accept. There are a lot of parameters that can be defined as habitable zones. Elemental quantity, surface in the atmosphere, the ultraviolet radiation, all other kinds of radiation. These things you can define maximum and minimum, and they could be defined as habitable zone also. They don't overlap with the water habitable zone very well. Absolutely, yeah. Not say the habitable zone based on water. Yeah. A very good point being made there about the naivete, really, of the habitable zone that we always roll out in these diagrams, where liquid water can be had. Well, you mean like Enceladus? Oh, yeah, right. If you've got ice on top of the thing, you could have liquid water almost anywhere. Pluto could have liquid water in it. Why did we draw the diagram the way we did? The answer, and this is true for most of the problems in the world, is artists are to blame, meaning a convenient, simple way that people instantly get. When we say water, we need water for life. What does that mean? It means an exposed ocean of water in temperatures like we're used to. Well, they're finding out the greatest amount of biomass on the Earth is in the Earth, meaning subsurface. The microbial life in the Earth's crust is vast, and we don't normally think about that. I'm leaving extremophiles out of it for the moment, but we really, there are so many possibilities for things like life, even without going to exotic chemical possibilities and so forth. Even without that, there are so many possibilities in space and different kinds of worlds that could offer different kinds of biospheres that our present habitable zone, we must understand, is a simplified convention only for finding a world very much like the Earth. But the Earth may not even be the best way to do it. It may be the atmospheres of Jovian planets are the best answer, absolutely. Maybe we'll find out that's the case. I don't think so. But you're right. We're learning what's really out there. And a lot of our ideas may seem provincial, naive, and kind of cute another century down the line. I think that'll probably be true. Oh, yes. Sorry. Ah, all right. I like this. I like that. You asked a great question there. Can planets form without a star? The official answer is no. Every source I hear says you need a certain large mass to attract gravitationally a sufficient amount of material, and that amount is a star to get a circumstellar disk going around it that will compress down into planets. but I have my completely unrealistic expectations. I'm an artist. I'm not a researcher. I can say these things. I think you can form planets directly out of the interstellar media by very, very slow condensation directly from interstellar clouds. I think that's the case, but having an opinion is not the same thing as science. It has not yet been demonstrated, modeled, or proven. So true astronomers right now would actually tackle me and hold me to the ground so that I could not say such things. It's not science yet. It's just an opinion. Is that it? Okay. Let's go ahead. Are there no one more? Can we try one more? Do we have
no.
any more? We don't?
No, it's all good on
All right.
online side.
Fantastic. Then I'll say thank you very much to all of you online and in the theater as well. Thank you very much.
Thank you very much, Chris, for a great presentation. There are a lot of kudos coming your way online as well. Just off the talk. So Chris has graciously agreed to let us keep the online. So if you're interested. So Barbara, are there any things that you would like to announce before I end the online portion of the meeting?
No, I think we're good to go. And happy holidays, everybody. And we'll all have a fond farewell to 2023 and a fond welcome to 2024. See you all next month.
Thank you. Thank you very much. On that note, bye-bye, everybody.